Okay, so now we're going to implement the model, the Ising model, using D-Wave. So here you can see the Ising model that we came up with as part of the last content. So 2 S1 S2 plus 2 S1 S4 plus S2 S4 plus S1 plus S2 minus 2 S3. So that's the model that encodes all the possible configurations of couriers and how that meets the requirements. So now the only thing left would be to implement that using D-Wave and try to find the solution. So we're going to start by importing from D-Wave samplers, import simulated annealing sampler. And then we will go ahead and implement the model again as using dictionaries. Instead of using a single dictionary to implement the entire Cubo model, in this case we need two dictionaries, one for the linear terms, another one for the quadratic terms. So the linear terms, usually that structure, which is a vector, is called H, so we will do the same for the Python dictionary. So for S1 you can see that the associated coefficient is 1. For S2 is also 1. For S3 is going to be -2, as you can see up here. And for S4 is going to be 0. Then we would have J, which is used for the quadratic terms. The quadratic terms need to be provided within tuples, S1 and S2. We have a value of 2, as you can see here. For S1 and S4, you would have a value of 2, and for S2 and S4, you would have a value of 1. Oh, sorry. Okay, then number of reads, 5000, sampler, simulated annealing sampler, and then response sampler.sample Ising. In this case, they have a dedicated method for Ising models. You need to provide the H, the linear terms, then the quadratic terms J, and the number of reads. Response.aggregate, that should be stored somewhere, and then the rest is going to be the same. So for values, energy, and number of occurrences in response.data, we want to convert the variables, or let's say select those that are actually relevant. So for key in values, if values key is not equal to -1, because in this case, let's visualize this first, print values, energy, number of occurrences, and you will see that in this case it's going to use values of 1 and -1 because we're working with Ising models. So you can see here the energies. There are 3 instances with an energy of -5. We can see the number of occurrences over a total of 5000. And then you can see the actual variables and whether the final value is 1 or -1. So we want those that are not -1 because in this specific problem, we want those couriers that should be selected. So I'm going to keep only the ones set to 1, and what I'm going to keep is the variable name, not the value. So if I move this here and say print variables, you can see how now I'm keeping only the variable names, the ones that are relevant, and I could even say print solution energy format variables. I'm going to put this aside, number of occurrences, num reads, and the energy. There you go, and that's it. So in this case, we are obtaining 3 different solutions, all of them with an energy of -5. In this case, we can see that we have the couriers 1 and 3, or 3 and 4, or 2, 3 and 4. Now, in this case, apart from the other options that we can see that are less frequent and are not relevant because they have a higher energy of -3. But the ones that have an energy of -5, if you were to study them, you would see that not all of them meet all the requirements, but at the same time, all of them have the minimum energy. There are several global minimums. So either you go through a validation stage in which you check whether each one of these solutions actually cover all the cities, or or you make sure that you redefine the model or adjust it in some way so that you get to the optimal solution. In this case, there is no perfect solution, so these are the three closest alternatives, and now it will be a matter of validating and selecting which one of them would be the best. But for now, we have been able to implement the model, the Ising model, and execute it with D-Wave, so that will be it for now. Thank you so much.